All right, all throughout this section, I get to play Captain Obvious because of these definitions. They're just so dull and obvious. But so yeah, we're going to be solving a variety of equations. We'll do them both algebraically and graphically. All right, not all of them. We won't do all of them on the graphing calculator, but we'll do those that I think are most important to do on them. Let's start with the definition of a radical equation. Okay, as you might expect, it's an equation that involves a radical. All right, that's a radical equation, and we have a few coming our way. If you look at the example below, we have a cube root expression in there, and that's obviously a radical. A lot of equations just have one radical involved. There are some equations, though, that might have two or more. So in this box here, I have a step-by-step process on how you would approach solving a radical equation, which is what we'd like to do with them. And with part A, it says isolate the most complicated radical. So that would be the case where when you're looking for a most complicated radical, that would be a situation where your equation has two or more radicals. And essentially, you would just look for the radical that looks a little more involved than any of the others. But with the equations that we're going to come up against, there's just one radical expression. So some of part A applies, and the part that applies is this one where it says isolate. So any radical equation, your first mission is to isolate the radical on one side of the equation. And if there's two or more, you want to isolate the one that has the one that looks more busy than the others. And the reason for doing that is because of part B, where you're going to eliminate the radical by raising each side to a power that is equal to the index. Okay, so as an example, let's say we isolated a square root expression. Let's say that that's equal to some sort of other expression. We'll call it C, I suppose. Then if you isolate your square root on one side of the equation, what you want to do next is square each side. And the reason for doing that is because when you square a square root, those two cancel out. Okay? And the reason why I use the square is because this is an implied square root due to there being no number written out on the little edge. Now, let's say that we isolated a cube root on one side of the equation. What would we have to raise each side to a power equal to? 3. Yep. You got it. Okay, the reason why we're cubing is because we're starting with a cube root. And when you cube a cube root, they cancel. And that generalizes to larger and larger indices. Now, once you get rid of the radical expression, there's usually a little more to do. All right, you end up with a different looking equation with possibly some more steps to go in order for to solve. So step C is just exactly that. You want to solve for the variable. Now there is this little warning down below. The warning is this: we might get what's called an extraneous solution when we work with radical equations involving an index that's even. Okay, so it says here, warning, extraneous solutions may occur when the index of the radical is even. So for example, if we're working with a square root, a fourth root, sixth root, so on and so forth. And what an extraneous solution is it's kind of like an extra answer for x that doesn't satisfy the original equation. Okay, so for instance, if we have to get rid of a square root, usually that means we square, each side to get rid of the square root, which usually creates a quadratic equation. And a lot of quadratic equations have multiple answers for x. Now, in some cases, one or more of those answers for x might not satisfy the original version of the equation, in which case it's one of these so-called extraneous solutions. All right, but that only happens when the index is even and you get multiple answers. All right, and if we get an extraneous solution, we just simply omit it from our final solution set. So with that, let's get to solving our first radical equation. So here we have 2 times the cube root of 5x plus 3 minus 4 equals 0. According to part A of the step-by-step process up there, we want to isolate the cube root expression. All right, currently it's got a couple of things happening, multiplication by 2 and subtraction by 4. What you want to do is get rid of the 4 first by moving it over to the other side. That's 2 times the cube root of 5x plus 3 on the left, equaling positive 4. And there's still one more thing being done to this cube root, and that's multiplication by 2. Any help on how we can get rid of this multiplication by 2? Yep, we can divide each side by 2. Okay, that cancels it out on the left. And on the right, 4 divided by 2 is 2. And the cube root expression is isolated on the left. There's nothing in front of it anymore, and there's nothing behind it. So this means it's fully isolated. So we've just completed all of part A. What does part B tell us to do next? Yep, we're going to cube each side. And I like how you put it in the chat bar, Isabel. We'll cube the left, which means we'll have to cube the right. And on the left, as we expect to happen, the cube root and the power of 3 cancel. 5x plus 3 is still left over, though, so let's keep that on the left. And on the right, 2 cubed is 8. And after getting rid of the cube root, it looks like we're left with a linear equation. And we discussed how to solve these last week. Start by subtracting 3 from each side to get 5x equals 5. Divide each side by 5. So according to our algebra, it looks like x equals 1 is our solution. A couple ways that you could check this answer. The first is to simply plug it back into the original version of the equation. Or what you could do is use your graphing calculator to verify whether or not x equals 1 is really the solution. So with that, let me jot this equation back down over to the right. We'll verify this using one of the graphing calculator techniques. Now, based on how the equation is written, which technique do you think we might want to go after? Do we want to use the intersect feature or the zero feature? Yeah, we might want to use the zero feature since we have the right-hand side equaling 0. So if we do that, let me just make a note underneath this that we're going to use the zero feature. We are going to define our y1 as the left-hand side expression. Get a coordinate plane going underneath it. And let's get to our graphing calculators. Show you how to type this in. All right, we'll go to the y equals menu. And in y1, we first need that 2 that's being multiplied to the radical. And for a cube root, you want to press the math key, which is in your first column. It's the 4th row down where it says math. And there are a few menus that you can go to after pressing the math key. We want to use the first menu, the math menu. And if you look in row 4, whether you have an 84 or a TI-83, there should be a cube root symbol. So you can scroll down to option 4 or just simply press 4 on your calculator. And it brings you back to the Y1 row. And I'm inside what looks like a cube root radical expression. If you have an 83 or a different software than I do on the 84, you might see a cube root symbol with half open set of parentheses, which is fine. So regardless, we do want to type in 5x plus 3. And if you have an 83 or if you have a half set of parentheses, now is the time to close off your parentheses. Okay, for those that are seeing what I'm seeing in my Y1 here, we're going to get outside the radical by pressing the right arrow button and then big minus sign 4. Everybody good so far? Okay, so let's look to see what the standard viewing window gives us. We'll do zoom option 6. And that thing is just creeping along. You can think about the SpongeBob narrator where it's like 2 hours later. But you guys seeing a similar picture to mine? Anybody getting something different? Nobody's calculator melted or anything like that? All right, cool. So it looks like there's a little bit of disconnect right here, but I will let you know that this graph is fully connected. The graphing calculator tends to struggle with pieces of radical functions that are very vertical looking. So I'm going to just connect everything together when I sketch this out, which I'll do that right now. Something like that. Y1, a little snaky looking graph. And I'll also indicate the standard viewing window settings as tick marks on the axes. Never a bad idea there. And it looks like according to our graph, there would be one solution for x. Okay, keep in mind with the 0 feature, we are looking for x-intercepts. And there appears to be one. So let's go back to the calculator. And we'll use the 0 feature. Second trace. And option 2. I'm currently on the y-intercept. Maybe you guys are as well. Okay, blinking cursor on the y-axis for me. And that's actually in a good spot for a left bound because it's to the left of where the graph is crossing the x-axis and it's somewhat near it. So I think I'm just going to press enter right off the bat. Now for a right bound, we want to go on the other side of the x-intercept, which is going to push you up above the x-axis a little bit on the graph. Okay, so maybe somewhere right here. Press enter. And then remember for your guess, you want to scooch it a little closer to the x-intercept, and you're also going to be in between the arrowheads that are pointing towards each other, just like my kids do when they try to blame each other for something. So I'll get near it and press enter. And there we go. Okay, can anybody confirm the 0 at 1, 0? Sweet. You guys rock. Left bound, right bound, and 1, 0. Okay, always the x-coordinate of these points of intersection or intercepts. So x equals 1 is confirmed. Any questions? All right, let us, as in the produce department, move on to the next page. For example B, anybody want to offer how to start this thing out?
Add -2 to the other side.
There you go. Yeah, we'll go ahead and Amazon Prime that over to the right. It does become positive 2. So square root of 14x minus 21 equals x plus 2. All right, so we get an expression on the right-hand side. And it looks like there's nothing in front of the square root, and there's no longer anything behind it. It is a square root, so let's think about getting rid of the square root. What should we do to each side to get rid of that?
Square it.
Square it. You got it. All right, so we know what's going to happen on the left. The square root and power 2 cancel, leaving behind 14x minus 21 equals, now we got to be careful here. It's very tempting to think that this is x squared plus 4, but I'll tell you right now that that's not what that equals. This power of 2, just remember guys, this means that we're going to have to FOIL, okay, meaning that there are 2 copies of x plus 2 being multiplied together on the right hand side. Now when you FOIL that, you're going to get x squared plus 4x plus 4, and you'll still have 14x minus 21 on the left. Everybody good with all that so far? So you'll notice that we end up getting a quadratic equation. No more radicals, right? But it does up the degree on x, all right? Now, my recommendation is when you end up getting a quadratic equation at some point during your solution to one of these radical equations, the best thing to start off doing is setting one side to 0. And the easiest side to set to 0 is the left-hand side in this case. And we'll see why in just a moment. To set the left-hand side to 0, we'll have to subtract 14x, and we'll also have to add 21. Okay, so we'll knock 2 birds out with 1 stone, or if you're Chuck Norris, he knocks 2 stones out with 1 bird. That means we'll have to subtract 14x on the right-hand side, and also add 21. These cancel. Get 0. And on the right, x squared minus 10x plus 25. So the reason why I want one side 0 is just in case the expression on the right, the quadratic expression, factors. Okay, if that quadratic expression factors, that's going to be your quickest way of solving for x. If it doesn't factor, then you'll want to use the quadratic formula. Okay, but what do you guys think about x squared minus 10x plus 25? Is that something that can factor?
Yeah.
Yeah, totally. That factors as x minus 5 times x minus 5. Okay, because negative 5 times negative 5 give us 25, and they also add up to negative 10. You guys remember what to do if we have a side factored and the other side is 0? Something special that we do with each factor. What you end up doing is you take each factor and you set it equal to 0. Okay, this is called the zero product property, or ZPP for short. And solving for x, we get duplicate answers of x equals 5. So any questions so far? All right. I do want to let you know that this is a radical equation involving an even index. And we got 2 answers for x, but they're duplicates. So there's a good chance that this answer of x equals 5 is legit. okay? But if we were to get something like x equals 5, x equals 1, just throwing a random value out there, then there's a chance that maybe one of those is extraneous. But either way, we're going to verify what the solution really is, okay, using our graphing calculators. So over to the right, let me just jot down the original equation. And based on the original version of the equation, which calculator feature do you think makes the most sense, the intersect feature or zero feature? So the zero feature would be if one side was the number 0. Yeah, I would go with intersect on this one. Nice try, though. You could force the zero feature if you wanted to by moving the x over to the left. But I'm going to stick with the original version and attempt the intersect feature, which is going to require 2 equations. Okay, the left-hand side, which will be our y1. And the right-hand side, which will be our y2. Oops. All right. Guys ready? Here we go. All right, so let's go to y equals. We'll clear out the equation for y1. Here's how you're going to get a square root. All right. You want to press the second button. Okay, so the second key right here. It's either blue or yellow for you. And you'll go down in this column to the x squared button. And by pressing that, you should get a square root symbol. And the reason why we're pressing the second key before that is because we want to access this little radical symbol that's written out above the x squared button. Now with me, I'm inside the square root symbol. If you have an 83 instead of an 84, you're seeing a square root symbol with a half set of parentheses. Either way, you want to go ahead and type in 14x minus 21 and either close off the parentheses or hit the right arrow key. Minus 2, big minus sign. Jump down to y2, type in x, and we'll do zoom, option 6. How's that look? Pretty radical, huh? Very good. All right, so here's the graph of y1. Okay, kind of hooks off to the right, and then our graph of y2 appears to be a line, and it does look like there's a point of intersection. Reason why it looks like there's a lot perhaps is just because the graphics aren't that good on the screen, but at least it looks like they're intersecting each other, and I'm gonna guess maybe somewhere in the middle of what looks like an overlap. So let's use the intersect feature by pressing second trace, and intersect feature is going to be option 5. And I don't see my blinking cursor, but if you look at the bottom of your screen or my screen, it is saying that we're at x equals 0, but at the top it's saying we're at x equals 0 on the first graph, which the graph actually doesn't start with x equals 0. It starts with an x value that's probably a little larger than 1. So to get this blinking cursor on the screen, let's just hit the right arrow key until we see something show up. And after a few clicks of the button, it does end up on the screen, and we're able to move it along this graph. Now remember, with the intersect feature, you don't really have to answer these questions. You just move your blinking cursor to near the area where they're intersecting and press enter 3 times in a row. So my calculator is probably having a little tiny rounding error. I get 4.999 and then y coordinate 4.999. Now, you know, if we were to write this number out, we'd have to round to 2 decimal places, which will, you know, obviously force our x value to round to 5. So maybe some of you are getting that a little bit of rounding error, 4.999, and maybe some of you are actually getting 5 itself. But either way, are we getting x values, either 4.9 repeat and or x equals 5? All right, cool. So you got x equals 5 and y equals 5. All right, but I think that's probably good enough evidence to confirm our answer of x equals 5. Let me just go ahead and sketch out these graphs. Hang on, pen froze on me. There we go. Okay, so the graphing calculator confirms our answer of x equals 5. We really only need to cloud in one of those duplicate answers. And how would you guys feel about trying one on your own? Let me give you a different equation. I'll add a part C in here. And the equation I'd like you folks to work on for the next 5 minutes or so, it would be 3 plus the square root of 3x plus 1. Okay, all that's on the left, and on the right-hand side, we'll have x again. All right, so I'm going to give you some time to work on this equation. First, solve it algebraically, so by hand like we did above, and then see if you can get the graphs going in the graphing calculator to confirm your answers. All right, so I'll check in with you in just a little bit. All right, I'm going to start jotting down my steps. Let me know if you have any questions along the way. All right, what do you guys think so far? Did you get x equals 8, x equals 1 with your algebraic solution? Okay. Now do keep in mind, well, very good by the way, so nice job folks. Do keep in mind that we are working with another square root, and we're getting two answers for x based on our algebra. And the reason for that is because at some point this turns into a quadratic equation. Now, as I mentioned, if you get multiple solutions for an even index equation, you want to look out for extraneous solutions. So doing this graphically would help us to see whether or not we have any of them. So let's go ahead and look at the graphs. I do recommend another intersect feature approach. Okay, y1, the left-hand side. So do be sure to use the original version of the equation. I'm doing this because when we check our answers the old-fashioned way, that's the equation we plug them into, the original one. Okay, so I'll go to graphing calculator. So 3 plus the square root. So remember, press the second key and then the x squared key for your square root symbol. We have 3x plus 1 in there. And we'll jump down to y2 and type in x. Zoom option 6. And here are the two graphs. Based on our graphing calculator, how many solutions should there really be? There should just be one solution. So it appears as though we have an extraneous. So it's kind of like a bonus answer for x that actually doesn't work in the original equation. So obviously we want the answers for x that work in the original version of the equation. So yeah, one solution, and you can probably tell which x value is the correct one just based on the location of the intersection. But let's go ahead and find it anyway. I do about 1 billion clicks over to the right to get over to that point of intersection. And press enter a few times. Yep, 8, 8. So it looks like our answer of x equals 8 is the real deal there. Here's graphs. Okay, the x coordinate is our answer. And over here on the left, x equals 8 is good, but x equals 1, I'm going to cross that out and just indicate that it's extraneous. All right, how we doing? Is there anything I can clarify, or is this all making sense so far? Any questions? All right, let's move on to our next type of equation, and that would be an absolute value equation. So here I really felt compelled to put Captain Obvious in the notes here. another obvious definition. So an equation that involves an absolute value expression is called an absolute value equation. Okay, so they're pretty easy to spot, much like the radical equations are. And there is, a step-by-step process that we can take in order to solve them by hand, and we can also verify our solutions graphically. And we'll do both with example part B. With example part A, I gotta fix one of the expressions in there, but when the time comes, we'll just solve example A algebraically and leave off the graphical solution. But to start things out, to solve absolute value equations algebraically, it's very similar to what we were doing with the radical equations. We isolate, in this case, the absolute value expression. Okay, so we want to get the equation to look like the absolute value of, let's say, an expression ax plus b equals, say, a number c. Now it says if the absolute value expression is equal to a positive number, then what we do is we apply a rule. So let's assume that this number on the right-hand side is positive. And if that's the case, then we get to break this equation up into two equations. And the first equation will get rid of the absolute value symbols, and it sets that expression that's inside of it, ax plus b, equal to that number c. The second equation, and let me go ahead and stuff the word or in there, the second equation takes that expression again, ax plus b, but sets it equal to the opposite of the c value. Okay, and the reasoning for that is because when you have the absolute value of a number, it represents the distance away from zero. So let's say that we had an absolute value of an expression equaling 5, then there are two possible answers for what could be on the inside of the absolute value. We could have positive 5, or we could have negative 5, because both the absolute values of those equal 5. So you apply the rule, all right? And once you do that, you solve for the variable in each equation. Okay, so there's usually a little bit more to do after you break up the absolute value expression into two equations, right? But the most important thing, in my opinion, is the fact that we have to do just that we have to separate the equation into two separate ones. And you'll notice that in each of these separate equations, the absolute value symbols are gone. And that's actually kind of one of our goals, is we want to get the absolute value symbols gone. And we can do that by applying this rule. So let me show you how this works with example A. I did want to make this 8 negative, so if you could do me a favor and put a negative in front of that 8. And we'll go ahead and solve. So here's our absolute value expression. It's not isolated because we have 5 minus that expression. First thing you're going to want to do is subtract 5 from each side to get negative absolute value of 4x is equal to negative 13. I want you to tell me, is the absolute value expression isolated after that one step? Nope. So what do you think you might want to do next? On the left-hand side, you can interpret this as like -1 times the absolute value of 4x. Yeah, exactly. So we can undo multiplication by -1 by dividing each side by -1. That will make the sign in front of the absolute values positive, and on the right, -13 over -1 gives us +13. So the absolute value expression is isolated, nothing in front anymore, nothing behind, and the number on the right is a positive number. So because of the current state of the equation, we get to split this up into two equations. The first will take the inside expression, set it equal to 13. And the second equation will set 4x equal to -13. And you probably know what to do with each of these equations. You can divide each side by 4. One answer for x is 13 over 4. Another answer for x is -13 over 4. Any questions about this example? All right, so can I have you try part B? Let's go ahead and see if you can solve part B algebraically, and in a few minutes I'll put my details up there, and then I'll show you how to solve this thing graphically. All right, so let me go ahead and show you how I did it. First divided each side by 2. Absolute value of 1 minus 2x is isolated on the left-hand side, nothing in the front or in the back. The number on the right-hand side is positive, so we get to split this up as 1 minus 2x equals 3, or 1 minus 2x equals -3. I'll go ahead and subtract 1 from each side in the first equation to get negative 2x is equal to positive 2. And can we confirm an answer of x equals negative 1 as one of our solutions? Sweet. We perform the same algebra with the second equation, but get a different answer. How does x equals positive 2 look? All right. So as advertised, we're going to do this one graphically as well. Let's look at the original version of the equation, 2 times the absolute value of 1 minus 2x equaling 6. Based on the format, looks like we might want to use the intersect feature. Okay, so that's going to require 2 graphs. In y1, we'll enter 2 times the absolute value of 1 minus 2x. And in y2, we'll enter in 6. All right, y equals menu. Let's clear these equations out. So we do need a 2. And for the absolute value symbol, we'll hit the math button again. And this time we'll go over to the num, which is short for number column. Which, by the way, after all this math, that's probably how my brain is going to feel, a little numb. I don't know about you guys, but anyway, option 1 has the letters ABS, that's short for absolute values or anti-lock brake system. Just kidding. But this is where we'll get the absolute value symbols. That's in the case of the TI-84. With TI-83, you might just be seeing the 3 letters ABS with half set of parentheses. All right. But either way, we'll be good to type in 1 minus 2x. Okay, if you're seeing ABS, 1 minus 2x, go ahead and close off the parentheses just for good practice. And we'll bounce down to y2. We'll type in the number 6. And we'll hit zoom option 6. There's the graph of y1. And there's the graph of y2. Okay, so you guys getting similar looking graphs? All right. Okay, so just in the interest of time, I will go ahead and provide you these points of intersection on my sketch. So since there, since there are 2 points of intersection, that does confirm 2 solutions. Okay, we got x equals negative 1 and x equals 2. And the first point of intersection, the one that's to the left, is at negative 1 comma 6. And the second point of intersection is going to be at 2 comma 6. And of course, it's the x coordinates that serve as our answers. And our graph confirms x equals negative 1 and x equals 2. All right, any questions about absolute value equations? All right, so let's move on to our last one, our last type of equation. And we can move on to the workday. The last Captain Obvious statement for this section of notes. An equation that can be solved by factoring is called a factorable equation. And these things are very similar in how we solve quadratic equations by factoring. We essentially want to get one side to be the number 0 and factor the other side as far as we can, and then we just set each factor to 0 to continue on from there. So sorry about the typos here. There are 3 overarching steps to this all. And in step A, you want to rewrite the equation so that one side is equal to 0. The reason for that is because we need to factor the resulting expression that's on the other side. And blending parts A and B together, once we've factored and the other side is 0, we set each factor equal to 0 to solve for the variable from there. Okay. Let's start with example part A. We have x cubed equals 81x. Now, according to step A, we want to rewrite the equation so that one side is 0. Now, the side that I usually set to 0 is the one that has the smaller power of x. Okay, so we have x cubed on the left and then x to the first on the right. So I usually will take that term with the smaller power over to the other side. In this case, it's via subtraction, so it's going to be x cubed minus 81x equals 0. And we have the 0 on the right-hand side. Now keep in mind that these are supposed to be factorable equations, so the expression that's on the left-hand side, we should probably anticipate being able to factor. Now if you look, we got x cubed minus 81x, and there are 2 terms here, both involving the variable x, so there's a GCF that we can factor out. And when we do so, we get x squared minus 81 remaining inside the parentheses. Now, x squared minus 81, I do want to point out that 81 is the same as 9 squared. So we do have a difference of 2 squares that's left over inside the set of parentheses, which means that we can factor further. Here's the x that came out in front at first. And x squared minus 81 will factor as x minus 9 times x plus 9. And there's no more factoring that occurs here. Okay, everything is as factored as it could be. And that takes us to step C, where we're going to set each factor equal to 0, including the x that was our very first GCF. Okay, now when you set x equal to 0, you do get one of your answers immediately. You do have to set x minus 9 equal to 0, which will give us a second answer of positive 9, and then x plus 9 equals 0, which will give us an answer of x equals negative 9. Does that make sense? Do you guys have any questions about that? There's really nothing more or less to solve, in solving these things. It's just a matter of setting one side to 0 as far as possible. But any questions on part A? All right, let's do part B. We do need to set one side to 0. We have smaller powers of x on the right-hand side. So everything that's on the right-hand side, let's bring that over. So x cubed minus 3x squared minus x and positive 3 when they come over from the right-hand side. And then we have 0. Now with the expression on the left, it is a 4-term polynomial. So any suggestions as to what factoring technique we might want to start out with, since there are 4 terms? Starts with a G. Yep, grouping. So we'll group together the first 2 terms. And keep in mind the third term is negative. So we want to be sure to include the minus sign when we group off our last 2 terms. And with factor by grouping, we want to look for GCFs within each set of parentheses. What's the GCF in the first set of parentheses?
X squared.
You got it. You factor that out, you're going to get x minus 3 left over. And our GCF from the second set of parentheses is, I would recommend taking out a -1. Okay, because when you factor out a -1, the terms on the inside will change to their opposites, so positive x and -3. And remember, with factor by grouping, we can go further when what's left over matches. All right, so I'm going to give you the next couple minutes to wrap this up. Okay, and once time is up, I'll include my solution and we'll go over any questions. And once all those are taken care of, we will move on to the next part of class. All right, so I'll check in with you in just a couple minutes. All right, so we'll factor out x minus 3, and we'll have a second factor consisting of x squared minus 1, which 1 is the same as 1 squared, so we actually have another difference of 2 squares. We'll factor as x minus 1, x plus 1. And just like in the last problem, we can set each factor equal to 0 to solve for x. Hence why it's called the factorable equation. Okay. We're going to get 3 answers for x. X equals 3, x equals 1, x equals -1. All right, do I have confirmation on these 3 values? Okay,